Hi students, welcome to Sunil's tutorial. I'm Sunil Nirvani and today we'll be doing this chapter called as sound waves. Please take down. Suppose if I have a wave, I could have a wave in this form or I could have a wave in this form. Right? How do I define a wave? These are two forms. You could have it in multiple forms. I've just shown you two forms. How do I define a wave? A wave, guys, is defined as an oscillatory disturbance. As I speak, if when you are speaking, if you hold your hand very close to your mouth, you will feel that there's a force that is being exerted on your mouth, right? So when you speak as with the hand very close to the mouth, and if you speak in a large volume, right, on a high pitch, you will feel that there's a force that is being exerted on your hand. That force causes an oscillatory disturbance which travels through the medium without changing the form, and that is what is called as wave. So what is a wave? It is an oscillatory disturbance which travels through the medium without a change in form. Let's write this, guys. Wave. Definition. How do I define a wave? A wave is defined as an oscillatory disturbance. Please write this down, guys. An oscillatory disturbance which travels through the medium without change in form. That's how you define a wave, right? Do we get this in clear? Now when we talk about waves, how do I classify waves? This is definition of waves. How do I classify waves? Waves are classified into mechanical waves and non-mechanical waves. Waves, when you classify them, they are classified into mechanical waves and non-mechanical waves. Right? Now, what do we understand by mechanical waves? Mechanical waves are those waves which require a material medium for their propagation. Propagation means to travel from one place to another. If I am speaking here, this sound should reach that person there. For that, they require a medium. So waves which require a medium so that they can travel from one place to another place are called as mechanical waves. Waves which do not require a medium to travel from one place to another are called as non-mechanical waves. Let's write this down, guys. Mechanical waves. What are mechanical waves? Which require a material medium for their propagation. So these are called as mechanical waves, right? Then similarly, what are non-mechanical waves? Non-mechanical waves, these are waves which do not require a material medium for their propagation. Which do not require a material medium for their propagation. Right? This is what is mechanical waves and non-mechanical waves. Right? Now, let's talk about mechanical waves. In mechanical waves, a medium is required for propagation. Right? Now, when you talk about medium, what are the characteristics that a medium should possess? Characteristics of medium. I want sound to travel from I want sound to travel from one place to another. right, for which I need a medium that will carry the sound from one place to another. So what are the characteristics that that medium should possess? Like air. Now start thinking about air. What are the characteristics that air possesses? The medium should be elastic, because once I speak, once the sound waves move from one place to another, there should be no sound here. It should regain, the particles should regain their original position. So the first characteristics is that the medium should be elastic. Fine, do we get this thing clear? So that it can regain its original condition as soon as the waves pass through. Second, the medium should possess inertia. Unless until it possesses inertia, it will not be able to propagate the waves. And third, the frictional resistance must be very small. Otherwise, what will happen is, if the frictional resistance between the particles is very high, the sound will not reach a distance only. Right? The entire sound will be used off in that, entire sound energy will be used off in that frictional resistance only. So the third characteristic is that the frictional resistance should be very small. Right? So these are the characteristics of medium. Next, what do we understand by progressive waves? What are progressive waves? Waves which continuously advance through the medium are called as progressive waves. Right? Which keep moving through the medium are called as progressive waves. If I speak here, and if this wave can travel from one place to another and will keep moving, then such a wave would be called as a progressive wave. Right? So what are progressive waves? Which continuously advance through the medium. Waves which keep continuously moving through the medium are called as progressive waves. Now when we talk about progressive waves, how do I classify progressive waves? Progressive waves are classified into two types. They are classified into transverse waves and longitudinal waves. Transverse waves and longitudinal waves. Right? Now, what do we understand by transverse waves? Let's try to understand this. This is time, this is my amplitude, plus A minus A. Now see this. What is the direction in which the wave is moving? The wave is moving in this direction. As it moves, it is going to create an oscillatory disturbance in the particles. In which direction will the particle move? In this direction here, in this direction here, in this direction here, in this direction here. You will see that in all the cases, the direction in which the particle moves and the direction in which the wave moves are perpendicular to each other. The direction of the propagation of the waves is perpendicular to the direction of the oscillation of the particles. Right? Such a wave is called as a transverse wave. So what is a transverse wave? A transverse wave is a wave in which the particles of the medium vibrate in a direction perpendicular to the direction of propagation of wave. Right? So that is what is called as a transverse wave, where the particle moves in a particular direction and the wave moves in a direction which is perpendicular to it. So particles and the waves are perpendicular to each other. Such a wave is called as a transverse wave, right? Next, what do we understand by a longitudinal wave? What do we understand by a longitudinal wave? Now let us see a longitudinal wave. Right? In a longitudinal wave, this is how the particles are moving. Right? This is how the particles are moving. How are the particles moving? The particles are moving in this direction. This is time and this is your frequency. Okay. How are the particles moving? The particles are moving in the direction, in this direction, and the wave is also moving in the same direction. So in longitudinal wave, what happens is that the particles and the propagation of the wave is in the same direction. The particles move parallel to the direction of the propagation of the waves. The oscillatory disturbance and the movement of the wave are in the same direction. So how do I define a longitudinal wave? A longitudinal wave in which particles of the medium vibrate in a direction parallel to the direction of propagation of wave. Right? That is what is called as a longitudinal wave. Can we get this thing clear? Now, let us see what are the characteristics of a transverse wave. Let's try to understand the characteristics of a transverse wave. This is your transverse wave. This is time and this is plus A and minus A. That's your displacement of the particle from the mean position. Right? Now, let's see what are the characteristics of a transverse wave. How do I understand this wave? Transverse wave propagation, in this method of propagation, as I told you by definition, the particles of the medium vibrate perpendicular to the direction of the propagation of the wave. First characteristic, particles of medium vibrate perpendicular to the direction of propagation of wave. That's the first characteristic. Now, second, the periodic time is same for all particles. All particles will take the same time to oscillate. Right? That means by the time this goes up and comes down, all the particles will take that same amount of time to move in that much direction. Right? The periodic time is same for all particles. Right? Next. Now, when a transverse wave passes through the medium, it is divided into alternate convex region and concave region. Right? See this. This is your convex region. This is your concave region. This is convex region and this is called as crest. This is your concave region and this is called as trough. So it moves in alternate convex and concave region, which is called as crest and trough. Fine, do we get this thing here? So let's see this. Transverse wave travels through the medium. Wave travels through the medium. Is divided into alternate convex and concave regions called crest and trough. Trying to get this thing here. So how do I define one wave? One wave is made up of one crest and one trough. One crest and one trough define one wave. Okay. One wave is made up of one crest and one trough. Right? The distance between two consecutive crests. See, suppose if I were to draw a wave like this. From this point to this point, the distance between two consecutive crests or two consecutive troughs is called as wavelength. Wavelength is denoted by lambda. So the distance between two consecutive crests or two consecutive troughs is called as wavelength. Distance between two consecutive crest or trough is called wavelength, which is denoted by lambda. Find V in this thing here. Next, the transverse wave can be directly presented in the form of a sine wave. Right? This particular form of wave, if I draw a wave for a sine function, sine of 0, 10, 20, 30, 40, this is the same form I get. So I can therefore say that the transverse wave can be directly presented by the sine curve. Fine, do we get this in here? So, do we understand the characteristics of a transverse wave? Now, let's try to understand the characteristics of a long. Yeah.
It's not the point of views, no?
I didn't get you.
Transverse
Waves can be directly represented by a sine curve. This particular curve is also called as a sine curve. This particular form of wave is called as sine curve. So what is the diagram that it has? It has the diagram of a sine curve. Fine, do you get this thing here? That's how you present a transverse wave. Fine. Next, let's move on ahead. Let's try to find out characteristics of a longitudinal wave. Characteristics of longitudinal wave. Now let's try to draw this guys first. So this is what a longitudinal wave would look like. Now first the definition. First characteristics is the definition. The direction of the propagation of the waves, this is with time. This is the direction of the propagation of wave, and the direction of propagation of the particles is same. Right? The direction of the propagation of the wave and particle is parallel. Right? So the first characteristics is that particles of the medium vibrate in a direction parallel to the direction of the propagation of the wave. Parallel to the direction of propagation of wave. Right, that's the first characteristic. Right? Now, like the transverse wave, the periodic time is same for all particles. All particles take same time to vibrate. So, same characteristics. The periodic time is same for all particles. Right, in the case of a longitudinal wave. Now, when the longitudinal wave travels through air, it has been divided into alternate compressions and rarefactions. Here you can see that in this region the particles have come very close to each other. Since the particles have come very close to each other, this is called as a compression. Here you can see in this region that the particles have gone further away from each other. Right? The distance is more than the mean distance. This is called as rarefaction. So, a longitudinal wave is made up of alternate compressions and rarefactions. Compressions consist of the region where the particles of the medium are crowded together, and rarefaction consists of the region where the particles of the medium are separated from each other. Right? Do we get this? Both the pressure and density of the medium is maximum at compression and minimum at rarefaction. So the wave is made up of alternate compression and rarefaction. Right? What is compression? Compression is where it is the region where the particles of the medium are crowded together. Compression is the region where the particles of the medium are crowded together. In short, the particles of the medium come close to each other. What is rarefaction? Rarefaction is the region where the particles of the medium are separated from each other. Right? Rarefaction is the region where the particles of the medium are separated from each other. So that is what is compression and rarefaction. Now, since the particles of medium come close to each other, they exert very high pressure. If they come close to each other, they are going to exert a force of repulsion on each other. So they will exert very high pressure. Since the particles of medium come close to each other in compression, there will be many particles in a small space, hence the density will also be high. So in the case of compression, the pressure and density is maximum, and in the case of rarefaction, the pressure and density is minimum. In compression, pressure and density is maximum, and in rarefaction pressure and density is minimum. Fine, do you get this thing here? Now, Guys, can you please see this? Can you see the diagram, please? The distance between two compressions or the distance between two rarefractions would be called as the wavelength. So how do I define wavelength in a longitudinal wave? Wavelength in a longitudinal wave is the distance between two consecutive compressions or the distance between two consecutive rarefractions. Fine? So write this down, guys. Wavelength is the distance between two consecutive compressions or rarefractions. Fine, do you understand here? Okay, so do you understand the characteristics of longitudinal wave, right? Now, let us try to find out the relationship between various parameters of a wave. Right, let's try to find out the relationship between V, F and lambda. Right? Now first of all, let's try to understand this. If I were to consider a transverse wave, this is my transverse wave. The maximum displacement of the particle from the mean position. This is the maximum displacement of the particle from the mean position. The maximum displacement of the particle from the mean position is called as amplitude. So how do I define amplitude? It is the maximum displacement of the particle from the mean position. Right? Amplitude is maximum displacement of particle from mean position. Which is the mean position? The x-axis is the mean position. Fine, do we get this thing here? Next, now the time taken to start the wave, go through a crest, go through a trough and complete the wave, that is one crest and one trough is one wave. The time taken to complete one wave is called as the periodic time or the period of the wave, right? Period, T. Amplitude is represented as A, period is represented as capital T. It is the time taken by a particle of the medium to complete one vibration. Time taken by a particle of medium to complete one vibration. Fine, did you get this thing here? That is my time period. Next, what do you understand by frequency? Right? Frequency. How many vibrations can I have in one periodic time is called as frequency. How many such waves can I have in 1 second? That would be called as frequency. See, this one crest and one trough is one wave. How many such waves can I have in 1 second? That is called as frequency. For example, if you consider electricity, if I put my finger in that and switch on, how many waves are coming from there? You have 240 waves coming in 1 second. Goes up, goes down, completes a wave. So you have 240 such waves coming in 1 second. If you are listening to the tabla, you have say about 300 waves per second. If you are listening to guitar, right? If you are listening to something like heavy metal, guitar, you have say about 13 to 14,000 waves per second. Do you understand? So that is the number of times that the particle of the medium vibrates in 1 second. So that is frequency. What is frequency? How many times the particle will vibrate in 1 second? Do you understand this? So frequency is the number of vibrations performed per second. Right? So frequency is defined as the number of vibrations performed per second. Now let's try to get the relationship. Once I know my basics, I can get my relationship. Now, I can say that the number of vibrations performed per second of the particle is called as frequency. Let us assume that T is the periodic time, one oscillation time. In one periodic time, I have one oscillation completed in time t. That was what was my definition of period. What was the definition of period? The time taken to complete one vibration. Right? Do we get this thing here? Hence, in 1 second, how many vibrations will be completed? In 1 second, I will have 1 upon t vibrations. But the number of vibrations per second is defined as frequency. Therefore, I can say that frequency is nothing but 1 upon t. That's how I get the relationship between frequency and time period. So frequency is denoted as n. N is equal to 1 upon t. So the frequency is defined as the reciprocal of time period. Fine, do we get this thing clear? Now, we also know that the distance covered by one wave, is called as wavelength, which is represented by lambda. Now let's try to find out velocity. Velocity we know is nothing but distance upon time. Velocity is v. Distance covered by one wave is nothing but wavelength. Time is the time period of the wave. So therefore I can say v is lambda upon t. Velocity is equal to wavelength upon time. But you can also say v is equal to lambda into 1 upon t. But we just derived that 1 upon t is nothing but frequency. So if I substitute this, I'll get velocity is equal to lambda into n. Thus you have the relationship v is equal to n lambda. Velocity is frequency into wavelength. Velocity is defined as frequency into wavelength. Fine, we get this in here. Next, let's see something else. Let's see Newton's formula. Newton's formula for velocity of sound. Let's try to understand Newton's formula for velocity of sound. Now, sound can be propagated in the form of longitudinal wave as well as transverse wave. Now, in the case of transverse wave, you have crest and trough. In the case of longitudinal waves, you have compression and rarefactions, as a result of which the medium, you have certain change in form in the medium, and the medium has to then regain its original form. Right? This suggests that the velocity of the sound in the medium depends upon how elastic the medium is. If the medium is more elastic, sound will be propagated to a larger distance. If the medium is less elastic, then the sound will be propagated to a less distance, because propagation of sound depends upon crest and trough and rarefactions and compression. How many rarefactions and how many compressions will take place will depend upon how elastic sound is. I can say that velocity of sound in a medium depends on the property of elasticity and density of medium. Right? So velocity of sound, how much or how fast it will travel, will depend upon what is the elasticity of the medium, how much wave the medium is allowed to pass, and what is the density of the medium. On the basis of this, Newton came up with a theoretical condition that he said Newton's condition is he said that velocity of sound is equal to square root of elasticity upon density. He said that velocity of sound is directly proportional to elasticity and is inversely proportional to density, and he came up with the condition that velocity of sound is equal to square root of elasticity upon density. Here in this particular formula, E stands for elasticity, rho stands for density, right? Now, sound waves in air consist of alternate compressions and rarefactions. Compressions are the region where the volume contracts, rarefactions are the region where the volume expand. Newton assumed that these changes take place at constant temperature. Sound waves in air consist of alternate compressions and rarefactions, where you have the volume, where volume contracts in compression and expands, right? This is how sound wave is propagating. Newton assumed that all these changes take place at constant temperature. Newton assumed that these changes take place at constant temperature, right? All these changes take place at constant temperature. He called this condition as an isothermal condition, right? Now, he also said that with this consideration, he said that volume elasticity, which is also called as, you will learn this later, bulk modulus. The volume elasticity of air is determined by its value equal to atmospheric pressure, right? The volume elasticity, here you have changes in volume taking place. How much is the elasticity of volume? Volume elasticity, in technical terms we call this as bulk modulus. Volume elasticity of air at constant temperature is equal to atmospheric pressure. Right? Thus, now I can substitute the value of elasticity with pressure. I can therefore say that E is equal to P. That means elasticity of air is equal to the pressure. So under isothermal conditions, that means under conditions of constant temperature, if E is equal to P, that means my formula will change as V is equal to velocity of air, velocity of sound in air. Instead of elasticity, I'll write P upon rho, right? But at NTP, normal temperature and pressure, NTP stands for normal temperature and pressure. At normal temperature and pressure, P is equal to HdG. Pressure of air is equal to height of the mercury column, density of air, and the gravitational acceleration, right? Pressure of air can be measured as height of the mercury column, density, and the gravitational acceleration. Now we know from experiment that the height of the mercury column in the barometer is 0.76 meters. Density of mercury is 13,600 kgs per meter cube. G we know is 9.8 meters per second square, right? And I also know that the density of air at MTP is 1.293, right? If I substitute these values in this equation, I have V is equal to square root of P upon rho, V is equal to square root of H dG upon rho. So I can say V is equal to, if I substitute these values, I will get that the velocity of sound in air is 280 meters per second. That's how Newton theoretically derived that the velocity of sound in air is 280 meters per second. How did he get that? By substituting those values in that equation. Fine. But when experimentally found out, V came out to be 331 meters per second, right? Thus, Newton's formula only gives you the theoretical value of velocity of sound in air. It is unable to explain the practical or experimental value of velocity of sound in air. There is approximately 16% difference between the theoretical and the experimental value of velocity of sound in air, which Newton's formula was not able to explain, right? With this, we'll stop this here for the day. Thank you very much.